Welcome back, Algebra Express. We are in the final chapter. So this is Rockswold 5.6. We're going to talk about exponential and logarithmic equations. So we're going to take everything we've been doing with exponents and logs, and we're going to start solving equations with them. The way that we solve equations is very similar to the way that we solved equations with weird functions before. So like when we had a square root, we had to isolate the square root. The approach is still very similar. We want to get things kind of by themselves and basically play the math bully, get them alone and by themselves, and then do the thing that undoes it, right? And so that's basically the first three, or the some of the three steps that they have here. The first one is to isolate the exponential expression. Then we want to take the log or ln on both sides. This is if we have an exponential. And then we're going to finish solving. If we want to solve a log, we're going to isolate the log, and then we're going to exponentiate both sides, and then we're going to finish solving. So basically vice versa if you're solving a log. Okay, so number one says solve, give an exact answer, and a decimal approximation to three places. So I have 2 plus 5 to the x minus 1 equals 12. So what is my goal here? It is to isolate the exponential expression. So my exponential expression looks like this thing. I want to get this thing by itself. What do I have to do here? There is this thing, and then there's 2 being added to it. So the first thing I would have to do is subtract 2 from both sides. So 5 to the x minus 1 is going to be equal to 10. Okay. Now there are a few ways you can do this, to be honest. This is my sort of approach. If I see a 5 here, and I want to get an exponent out of something that is base 5, typically what I will do is take a log base 5. And so if I take a log base 5 of the left side, I also have to take a log base 5 of the right side. So I'm taking a log base 5 of each side. If I look at this left side, and this is why I like to do log base 5, some people like to do other base logs. You can do other base logs. I think some people might do log base 10 and bring things down and do things like that. That's something that you can do as well. You should end up with the same solution. This is log base 5 and 5 to the something. And so now this is where those identities are coming in, like we talked about in the previous sections. If you can see these inverse identities, that's what you need to see to be able to simplify these things. So this is log base 5 of x minus 1 dx. Log base 5 of 10. Okay, so I have done the sort of what I want to say the hard steps in this thing, right? I've isolated my exponential. I've taken the log. So now I've gotten rid of all the weird things that are attached to my x. So now I just have something that looks like x minus 1 equals, and this is a thing, but it's a crazy number. It's an irrational number, but it's just a number over here. So what I want to do is I have this one, x minus 1 equals log 5 of 10. I want to add 1 to each side to get my x by itself. So log 5 of 10 plus 1. Okay, so if I want the exact, this is my exact right here. I have log base 5. And if I want a decimal approximation, I'm going to have to use the calculator, right? So if we use a calculator, we're using the change of base and we're adding 1 to it. So this, if you did it in a different way, this is where it would be matching up, I believe. when we do change of base, it's going to look like log 10 over log 5, which gives me somewhere around 1.43. I'm going to add 1 to it. It's going to give me somewhere around 2.43, and we want to round it to 3 decimal places. So it's about 2.31. Okay. So again, it's the same sort of approach when we were solving other functions that were looking weird. We get the weird guy by himself, we isolate him, then we do the thing that undoes him. So the thing that undoes an exponent is a log. And so that's their example of an exponential equation. Now we're going to go into logarithmic equations. It is the same approach. We want to get the log by itself. So you might notice this log, it has a coefficient maybe of like 1 out here, right? We want to get a log with nothing else there. So if you look at this example, it's the same as this example for some reason. There we go. It is the same thing. So let's look at how to do this. And they do things a little bit differently than I do. So they do them by like this definition that they were showing on the previous page. But the approach is still the same up until then. So if I want to solve this, I got to get my log by itself. So I have a log base 3 of x. If this is being multiplied by 2, I'm going to have to divide by that 2. So I'm dividing -2 by 2. I'm dividing both sides by 2 to get to here. And the book does a circling thing to get to the x. If you want to do that, you can do that. But if I have, I don't know, 3 squared and 3 to the x, what can I say here? I know that 2 would be equal to x. So if I have the same base and these two things are equal to each other, then I know their exponents also have to be equal to each other. So if I want to raise things to the same base, it will hold true that they are equal to each other. So I can exponentiate things and it should not change my equality is what I am saying here. So if I want to look at these as exponents, 3 to the log base 3 of x and 3 to the -1. And if you do things with the definition, you will get the same solution out of this thing. This right here, and I'm hoping you notice, is your inverse property. And if that's the inverse property, this is giving us x. This is 3 to the -1 power. So maybe I have to do a little bit of simplifying. 3 to the -1 is like 1 over 3 to the first, or 1/3. That solution is equal to 1/3. Okay, and just to recap what a solution is, if I go back and plug in 1/3 into this, it should give me a true statement. And to be fair and honest, we probably really should be checking these solutions. I'm not sure that they tell us explicitly to check it, but we really should be checking these solutions because the log does have some restrictions with this domain, right? The exponential, we talked about this, the domain of the exponentials like this would be all real numbers. But my domain, when I start talking about logs, right, is that this thing has to be greater than 0, right? So there are some domain restrictions that we might have to think about sometimes on these logs. I'm not sure if it comes up in any of these notes, but it is something that is out there. Same thing here. If I want to know the domain of this one, it would be 10x plus 1 is greater than 0. So I would have to do maybe a little bit of solving. 10x is what, greater than minus 1? Minus 1/10 is what it has to be. So if we get a solution that is lower than 1/10 or negative 1/10, we know we would have to reject it. The other way is we can go plug it back in and check. Here we'd have to get an x greater than 5, I believe. Okay. So we're looking at this. The first step is to get the log by itself. So we want to ask ourselves, is the log by itself? I don't have anything multiplying it. I don't have anything adding to it. There are things within the argument of the log, right? There are multiple operations in here, but that is okay. The log itself, or the log is by itself, right? This argument's part of the log. We look at this thing as kind of being one thing. We're just looking at the log. So now if I'm looking at this, I see a log base 5. So if you want to do their definition and do go 5 to the third, that's fine. What I do is I raise this as an exponent of a base 5. And if I do that, you might notice these two are giving me an inverse property. So this should look like 10x plus 1 on this side now. This should look like 5 to the third. Now I have something that looks like 10x plus 1 equals 5 to the third. 5 to the third is a number, so I can figure that thing out. This is 10x plus 1. I'm going to do my exponents. 5 times 5 is 25. And if I got 5 quarters, that's $1.25. Okay, now I am solving for x. So this is a first order linear equation. Ooh, I hope y'all know how to do these by now. So I have to subtract 1. X equals, we're going to divide by 10 to get 12.4. Okay. So my exact solution is x equals what? 12.4. And I did what? Decimal approximation. I guess we could also do 124 over 10. And try to reduce that if you want to give it as a mixed fraction or as an improper fraction. I think they're both divisible by 2, which will give me 62 over 5 if you want to do a fraction. This one's an even decimal. So this is also exact here. Either way is good here. Okay, now we got one more. Look at, ooh, no, we got 2 more. Sorry, trying to skip one. Ln of x minus 5 equals minus 1. Okay, so we're looking at this thing. And just to recap, I know it's weird, but this is kind of like we're doing log base e, right? So if Ln is messing you up, it is an e that is the base of this thing. And if e is my base, I want to raise these as exponents, or exponentiate these things as a base e. All right, so if I exponentiate these things as a base e, what we see here, hopefully, is that I have an e to the ln. And if I have an e to the ln, those two functions are inverse functions. They should inverse each other to where I get the thing originally plugged in, which is x minus 5. And this is equal to e to the minus 1. If I want to solve for x, I get the log by itself. I exponentiate things to get rid of the log. And now I should have something to where I could solve for x. So if I add the 5 over, I get e to the minus 1, what, plus 5. So if I want an exact, and they may or may not write this. I'm not sure what form the book might write this in. This is fine for me, but they might do 1 over e plus 5. I'm not really sure. Sometimes they don't like to do negative exponents. So if we had to make this positive, we could flip it over 1. But if we go and type this into our calculator, we're probably going to type e to the negative 1 power. And a lot of calculators differentiate between negative signs and subtraction signs. But e to the negative 1 is going to give me somewhere around 0.368. And I'm going to add 5 to it, and so I'm going to get somewhere around 5.368. And maybe I should just say these are x values that I'm talking about. This is my solution here. If you want to go plug this thing back into here, it should check out. Okay. Now we got one more. This is 3 log of 2x equals 6. Okay, so the first step is to get our log by itself. So is our log by itself? No, it's still got this 3 in front. So I want to, this is being multiplied by 3. I want to divide by 3 on both sides. So I'm dividing this side by 3 to get log of 2x. 6 divided by 3 should give me 2. Okay, now is our log by itself? It looks like it. This is a log base, if we don't see it, 10. And so now comes the weird step. The new guy on the block. We're going to exponentiate things with a base 10. If I look here, that is my inverse. That is giving me 2x. This is giving me 10 to the second power. If I'm looking along here, this looks like 2x is giving me 100 is 10 squared, and I can solve for x by dividing by 2. And if we go plug it back in, it should check. But the exact solution is x equals 50. 50 times 2 would give me 100. Log of 100 is 2. 2 times 3 gives me 6. So it should check out if we go plug it back in. Oh, compound interest now. So we have to remember what our compound interest formula is. How much time does it take an investment of 1,000 to grow to 8,000 at a rate of 9.5% compounded annually? So if you don't remember the formula, it might be a bit difficult, but it should look something along those lines, where P is the principal, A is the accumulated amount, 1 is the number 1, R is our interest rate as a decimal, and N is the number of compounding periods per year. All right, so this is our formula. We want to start plugging things in. How much time does it take an investment of 1,000 to grow to 8,000 at a rate of 9.5% compounded annually? So if you see compounded annually, this is giving us some information into N. So if it's compounded annually, now I can write N. So this is N equals, it's compounded once per year. This is my rate, but I have to do a little bit of converting. So 9.5% is 0.095. Now we got to know which one is our accumulated, which one's our principal. The principal is the thing that you're starting out with, is the $1,000, and the accumulated amount is here. So what this is saying is 8,000 is equal to 1,000. I have 1 plus R over N, which is 0.095, over N, which is 1. And this is 1. And my T is the thing I want to know. How much time? Okay, so there's maybe a little bit quick cleaning up. Since they gave us N equals 1, we should be able to do that pretty quick. Like 1 plus 0.095 is 0.095. We divide it by 1, it's still 0.095. And 1 times T is going to give us T. So this is the exponent that is giving us trouble. If you want to add the things in the parentheses, it might look a little bit better. You might be able to see it maybe a little bit better. But this is 1.095 to the T. I want to get my exponential term by itself. So this is the T in the exponent. This is the base that is attached to it. So this is the thing I want to get by itself. So if I'm looking here, I want to get this thing by itself. I'm going to have to divide each side by 1,000. So if I divide 8,000 by 1,000, this gives me 8. This gives me nothing left here. 1.095 to the T. And this is probably where I differ from some people in the way that they do it. But I'm going to take a log base of 1.095. My calculator will do it. It is weird. It is a little bit weird, but if you have the technology and it does it, go for it, right? So if I want to take log of 1.095 of 8, and I want to take log of 1.095 of 1.095 to the T. I want to do log both sides. This side is going to end up giving me a number. I might have to plug it into my calculator, but I can figure that out. This side, I did a crazy log because it would simplify this really quickly. So these two things are an identity. This should end up giving me T. Okay, so this is an exact solution. If we go back and tell them, if your boss asked you, let's reread what they're asking. How much time does it take this investment to grow from that amount to that amount with all those details, right? If someone asked you how much time does it take this account to grow, and you tell them T equals log of log base of 1.095 of 8, they would probably be really mad at you. That is not something you want to hear. So what we're going to have to do is a little bit of approximating. So if we do log of 8 divided by log of 1.095, it's giving me something like 22.91. And so this is close enough. This is about 23 years is what I would probably tell them, just to be on the safe side. I don't think it tells us what place to round to in this one either, huh? But if it's taking someone, what, 22.9 years, you could probably just tell them 23. It's pretty close. Okay. What is the doubling time of an investment with an interest rate of 8% compounded continuously? Okay. So now they want to know what the doubling time is. And keywords here is compounded continuously. So if we see compounded continuously, that is not the formula that I have written previously. That is the PERT formula. Okay, so what is the doubling time of an investment? So they don't give us, what you might notice is that they're not giving us an accumulated amount or principal. Okay. So what might we want to do then? So what we can do is we can come up with something. So if I want a principal of, I don't know, let's do 100. If I want that to double, it's going to be 200. My rate is here. We want to know the time. So I want to know the time it takes this thing to double. Okay, so let's do this. What, 200 is my accumulated amount is equal to 100. And you can really kind of, I picked 100 and 200. You could really kind of pick any two numbers you want as long as you're doubling them. And we'll see, hopefully in just a second, why that's true. 8%, so if I want my interest rate to 0.08, I have a T on here. So if we look at this formula and we recognize what's in this formula, this is the amount that I'm starting out with. This is the amount I'm ending in. This is the factor that I'm multiplying to get from here to here. So if we're solving this equation for t, the first thing we're going to want to do is isolate our exponential, which is the natural exponential there. In order to do that, we're going to have to divide by 100. So if you wanted to just set up your equation, and you recognize that this is your factor, and you wanted your thing to double, that would mean that this is 2. So if you wanted to just set it up here without coming up with amounts for principal and accumulated amount, this is exactly what it's asking. When is this factor going to be 2? Is like asking when is this thing going to double, right? So this thing is our factor, the e to the whatever the heck. Okay. If we want to get rid of an e, we get our e by itself. We want to get rid of it. How do we get rid of an e? We have to take a natural log. This is a natural exponential. We have to take a natural log. So if I take a natural log of 2, I take a natural log of e to the 0.08t. This is just going to give me a natural log of 2. That's a crazy number, an irrational number, but it's just a number. This is 0.08t. I use my inverse properties here. Now I want to solve for t. So I have to divide by 0.08. So t is equal to the natural log of 2, and I'm going to divide by 0.08. And again, if someone is asking you how long does it take my account to double? And you tell them t, the amount of time is ln of 2 over 0.08. They're going to probably look at you a little weird. So let's convert that to a decimal. So I'm getting t 0.66 or roundabout. Rounding it down a little bit. You could probably tell them 8.7 years. It'll be a little short of 9 years. Okay, and this again, you could throw any amount into here. It should work as long as this is double of this. This is double this. Sorry, I did that the wrong way. And the final problem. Okay, so they say recall tritium from example 5.3. The half-life is 12 years. The initial amount is 15 grams. And so they give you this formula. So again, this is the initial amount that we're starting with. If we're halving things, or this is a half-life, we're multiplying things by a half. If every half-life is 12 years, we have to divide the number of years by 12 to get each time we're going to multiply by a half. How much time does it take for the amount of tritium to decay to 5 grams? All right, so what are they giving us? What's variable? So x is the number of years. T of x would be the amount of tritium. So what they're doing is they're setting this up so that T of x should be 5 equal to 15. I get a half x over 12. So they give us 5 grams that this ends up with. They want to know how much time it's going to take. So we want to solve this thing for x. So they're giving you a word problem with the setup to make it an exponential equation. Now we're looking at this thing here. We want to get our exponential by itself. So in order to get our exponential by itself, first thing we're going to have to do is divide by 15. So 5 over 15 equals 1/2 to the power of x divided by 12. 5 over 15, I'm going to simplify that real quick. This is 1/3. X over 12. Okay. Now that I'm looking at this, my goal is to get my exponential by itself. After I have my exponential by itself, I can start taking logs to get rid of my exponential. So I want to take a log, and to be honest, you can use any base log. Some people like to do log base 10 and then use their exponent rules. I like to use this base log because it just gets there a little bit quicker. So if I want to do log base of 1/2, I'm going to do log base of 1/2 of 1/3. I'm going to do log base of 1/2 of 1/2 to the x divided by 12. And I took this crazy log base 1/2 because now these two things are the inverse property. This thing is equal to x over 12 on this side. I have a log base of 1/2 of 1/3. And now the final thing, if I want to solve for x, x is being divided by 12. I will have to multiply each side by 12. So x is equal to 12 times this thing, which is log of 1/2 of 1/3. Okay, so now I'm doing log of 1 over 3, and I'm dividing that by what? Log of 1/2 or 0.5. So again, we want to give them an answer in what? Years. So if you tell them it's 12 log 1/2, 1/3 years, someone's gonna be really mad at you. So let's not do that. So let's do this 12 times, and this is gonna be something like 1.58496. Approximately. Now I'm rounding things a little bit. And if I multiply these two things, I'm getting 19.019, something like that. 196. I guess I should round it up. Okay. So you could probably say about 19 years. If someone was asking me this, I would probably tell them it's a little over. Just to be on the safe side. Because if they get to 19 years and it's not to the amount that they want, they might be really upset, right? They're like, it's 19 years and you told me 19 years. So if you tell them a little over, they can't be mad if they get right to the 19 years and it's not exact on the dime, right? Okay, so that is the final problem. We just have a few more tests and that is it. So I will see y'all soon.